So this is the this is going to be a short lecture. I don't have. I nearly finished the course yesterday, but I didn't want to rush. So this is going to be a shorter lecture. We're going to discover a relationship, a very nice relationship between the Lorentz group, which we've seen is absolutely fundamental for special relativity, and another group, which is actually very simple and easy to write down. So I'll tell you what, I mean, it's the title of the section, so if you've got the lecture notes, you know what the other group is already, but I won't tell you yet. What I'm going to do is, first of all, I'm going to imagine I've got a vector in space-time. As usual, it's x0, x1, x2, x3. And I'm going to write it, I'm going to express the information contained in that vector in a different mathematical form. I'm going to write it like this. Where does the plus go there? So I'm writing it in the form of a 2 by 2 matrix. These numbers here are real numbers. So that is a real number, and so is that. But this, of course, is a complex number. That's the square root of -1. You notice that these two are complex conjugates of each other. And so you notice, therefore, that if you take the complex conjugate of the whole matrix, that's the same as taking the transpose of the matrix. So for this matrix, complex conjugate is the same as transpose. Okay, and I think I'm using the right terminology when that conditions. We use the name Hermitian for that. It's a Hermitian matrix. I think that's the right terminology. In fact, I'm going to do one more thing for a reason which is not obvious now, but happens later. I'm going to choose a scale here.
But you don't take conjugates in the main diagonal.
Yeah. So no. Well, I can, but nothing happens because it's real.
Okay.
Okay. I take conjugates of the whole matrix,
Okay.
but nothing happens here.
Okay.
Okay. But
Yeah.
right. And then for reasons which I don't need in this course, but are important elsewhere. In fact, it's conventional to pre-multiply by that scale. So what I've got here is a function, a mapping, which I call capital psi of xa is defined to be that. And so capital psi takes us from vectors in Minkowski's in R4, space-time vectors, in fact, to 2 by 2 Hermitian matrices. Okay. And it's 1-to-1. Or, if you prefer, injective. Why? Well,
Surjective.
yeah, injective. Okay, if you prefer.
No, but surjective also.
Yes. Yeah. Because you can start with one of these. If I started with one of these, then it would in general look like this, A, B, C, D, right? And if I want to recover the vector, then what I can do is I can add these two things, and that will tell me what x0 is. I can subtract them, and that will tell me what x3 is. And then the same for these two. So I can go that way as well. So it's, yeah, it's as you say, in fact, bijective. Okay, good. So this is, at the moment, this is just another way of recording the information in that vector. So why is it, why is it useful? Well, if we take the determinant of this matrix, so this means determinant, if we take the determinant of this matrix, then look at what happens. That times that minus that times that is x0 squared minus x1 squared minus x2 squared minus x3 squared with a 1/2. In other words, it's 1/2 of xa xb gab. It's a half of the square of the magnitude of the vector. So this is mapping from vectors to matrices records the vectors in such a way that the Minkowski length of the vector is the determinant of the matrix. So this is good, okay. Now what we do is we perform the following mapping. We take one of these matrices and we map it by multiplying by another matrix M on the left, and multiplying by the conjugate transpose M star. So that's conjugate and the transpose. Okay, on the right. So we're forgetting about x for the minute. It's there, but we're leaving it alone. We're taking this matrix, in other words, this matrix, and we're doing something to it. Namely, we're pre-multiplying by a matrix and post-multiplying by the same matrix, but conjugate transpose of the same matrix. What is this matrix? This matrix M, so where M is a matrix in the group SL2C. So this is the group which we're going to discover has a very...
It's a complex.
Yeah,
entries.
yeah,
Okay.
yeah. So this is the group of 2 by 2 matrices A, B, C, D with, so 2 by 2 matrices with complex entries. So these numbers are complex numbers, and the S means that the determinant is 1. Okay. So you choose any element of this group. It's a group by matrix multiplication. Choose any element of this group, do this to it, take its conjugate transpose, which of course is in general different from the original matrix here, and do that to it. And what you've got now is you've changed the original matrix over there to something else, okay? Using this, basically by choosing an element of SL2C. But now look at this result here, this right-hand side here. This is Hermitian. In other words, if you take the conjugate transpose, it does not change. If you take the conjugate transpose of the whole thing, then in fact, it does not change, right? So this whole thing is also Hermitian. Because the transpose changes the order, and then the conjugate changes the star back to M again, okay? So taking the conjugate transpose of the whole expression does not change it, and therefore it's also a Hermitian matrix. So this is a mapping from one of these Hermitian matrices to another one. But also, now look at the determinant here. If you calculate the determinant of this, you see these matrices have determinant 1. So the determinant of all of this is still 1, right? It was 1 there, and it's still 1. Whoops, I can't write. Determinant 1. So this one was Hermitian with determinant 1. When you do this to it, you get another Hermitian matrix with determinant 1. In other words, what you've done is you've got yourself, this is going to be the mapping applied to some other vector. Actually, I don't want to write that down like that. You've effected a transformation on space-time which preserves the determinant. Okay. Have I missed something out here? Yeah. So what you've done is you've effected this in effect is a linear transformation of the vectors in space-time, which keeps the determinant of this matrix unchanged, and it therefore keeps this thing unchanged, right? And it's therefore a Lorentz transform, okay? So this operation, choosing a matrix in SL2C and doing this with it, is in effect a Lorentz transform. Or to put that slightly more precisely, this operation gives us a mapping from SL2C to the Lorentz group. So that's the Lorentz group. And I want to, because given a, whoops, I haven't finished that bracket. Given a matrix in SL2C, given one of these things, you can use it to do this. And this is a linear transformation on space-time which preserves the Minkowski length, and therefore it's a Lorentz transformation. And in fact, it maps into that part of the Lorentz group which is denoted like this. I'll explain what that is next. So the Lorentz group comes in 4. So as a mathematical object, it comes in 4 connected components. Let me explain why that is. So if you've got a Lorentz transformation, maybe it preserves the direction of time, okay? Or maybe it reverses the direction of time. So that's what. So you could choose a Lorentz transformation. I mean, the ordinary transformation between S and S dashed preserves the direction of time, right? The rate at which the clocks are going is changing, but at least they're both ticking towards the future, okay? You could perform a reflection in time, and then that, of course, no longer preserves the direction of time. The other thing you can do, you can perform a reflection in space, which changes if S has a right-handed coordinate system, then in a reflection, to get S dashed, you'd have a left-handed coordinate system. In other words, the orientation, the spatial orientation of your geometry is the opposite one. And those two changes, time and space orientation, divide up the group into 4 connected components. And this is the one which preserves the time orientation and the space orientation. And this is the one which contains the identity transformation. The group must have an identity, and it's got to be in one of these 4 components. And sometimes this one is referred to as the identity connected component. Okay, and this mapping from SL2C into the Lorentz group takes you to this component. Okay.
I make a little observation. The quadratic form there,
Yeah.
which you know up there in the middle
Yeah.
board, okay?
Yeah.
However, the initial coefficient is not 1, it's C.
If you write this in terms of,
Okay,
yeah, I wrote x naught as CT.
it's CT.
Yeah, x naught is C. So x naught is CT, x1 is x, x2 is y, and x3 is z. So I've absorbed the C into this. Okay, just to get rid of it, basically.
It's a constant,
Yeah,
okay?
yeah, yeah.
Yeah, but one shall be slightly careful with that.
Yeah, you have to remember that you've done that. I agree. Yeah. Okay, now this mapping, so it wouldn't be any good, except of course it turns out it is a group homomorphism. So there's various properties. One property, it's a group homomorphism. Okay, I wouldn't be constructing it otherwise. It wouldn't be any use to us, would it? We wouldn't be able to compare the groups unless we've got a homomorphism from one to the other. So you can check that by going through some algebra. You take 2 elements of this group and work out the corresponding Lorentz transformations, and but it's not hard to do. It's a group homomorphism. It ends up in its image is in L up plus, as I said there. And thirdly, the kernel of the group homomorphism is either so you've got the identity matrix in here, plus or minus the identity map you to the identity Lorentz transformation. So the kernel, and you can see that quite quickly actually, if you obviously the identity maps you to the identity Lorentz transformation, but also minus I here and here. The minus signs cancel each other out, of course, and so minus the identity will also be in the kernel of this group homomorphism. Yeah, to see that it's actually surjective, we do some counting. So SL2C, how many parameters does it have? Well, it's got 4 complex numbers, so that looks like 8 parameters. But remember, its determinant is 1, so that's 2 real conditions, and so it's actually 6 parameters. And I didn't actually show this anywhere, but it's not hard to see that the Lorentz group is also 6 parameters. Okay, So you can see that in fact it must swallow up all of this. So it's except for the fact that you've got this doubling here, it's an isomorphism. It's a 2-to-1 isomorphism. And this doesn't prove it, but there's a fairly short argument, which I won't give now, that tells you that actually, from the point of view of, if you're looking at the Lorentz group and the way it changes your night sky, then it's easier to think of this group as acting. Okay, this is the group really which acts on your night sky, as we saw at the beginning of today and also in more detail yesterday. Now this relationship between these two groups, this is 2-to-1, this isomorphism here. Actually, I don't know who wrote it down, but I know that Penrose made a great deal of use of this very beautiful relationship between these two groups. Okay, well that's actually, I warned you that the lecture would be short, and that's it. If you want to read more about Einstein himself, in my opinion, the best biography of him is by Abraham Pace, P-A-I-S. It's in the lecture notes, and it's a book called "Subtle is the Lord," and it's a quotation from Einstein which continues, "Subtle is the Lord, but he is not malicious." Okay, and he was referring to some discussions actually to do with quantum mechanics. So for a biography of Einstein, that's really a beautiful book. I've already referred to a paper by Penrose which is called "The Apparent Shape of a Relativistically Moving Sphere." I mentioned that yesterday. The detailed reference is here. There's another amazing book by Penrose called "The Road to Reality," a fat book, which I thoroughly recommend. And finally, as I mentioned right at the beginning of the lectures, for sort of classical relativity, special and general, and also for some cosmology, the book by Rindler is wonderful. Thank you very much. Thank you very much, folks. So I'll see some of you next week. Oh, thank you.